Okay, so here's our code. Could you walk us through the code first?
So basically what we did is we made these for loops that are inside of each other.
Okay.
They were A, B, C, and D.
Uh-huh.
And they're just going from 1 to 10.
All right, and so what is that doing with A, B, C, and D?
So it's just, those are basically all our cases for our quadruples of A, B, C, and D.
Okay, do we ever overcount?
Nope.
Why not?
Because they're all distinct things. A, B, C, and D are all distinct.
Okay, good.
And then variable 1 is first side of the equation, A plus B times C times D.
So we got A plus B times C times D. And you always want to be careful because if you say B, C, D without the times here, maybe the computer thinks you just defined a new variable called BCD, right? So it's always, for me at least, it's always nice to actually just say the multiplication so that you know you haven't mistyped something. Okay?
And then variable 2 is our other side. It's A times B plus C times D.
Okay.
And then our if statement just says that if the two sides of our equation are equal to each other, then increase our count. And that's just going to tell us how many we have.
Okay, right. So the count starts at 0. Every time we have one, we increase the count.
Yeah.
And we see, and we're hoping we see 913, although this little highlighted in green makes me think we have the wrong number of parentheses, but we'll see if it runs. The only other thing I want to point out is when I'm defining a variable like here, you see I say that variable equals this.
Yeah.
When I'm checking an if statement, if I want to check if two things are equal to each other, do you understand why that's different?
Yeah.
So I've got a double equals.
You're defining that.
Sort of, yeah. I'm setting this variable equal to this expression. Here I'm checking, are these two variables equal to each other? I don't want variable 1 to equal variable 2. In other words, I don't want to set it equal to variable 2. I want to check if they're equal. That's why it's double equals there. Print count, and what are we hoping for?
913.
And we're also hoping for not an error. Right, 913. On screen? On screen. Okay, good. Now, one of the things you found was that when b equals 1, there were 729 solutions. How could I modify this code to find just those solutions when b equals 1?
Just take out the b equals 10, the b less than 10 part. Just say b equals 1.
Okay. But I want to keep it I want to keep the code as a for loop. So how do I only loop through one choice?
B equals 1, b less than 2.
Okay. And here we're hoping for 729.
Yep.
There we go. Now, when a was equal to 1, b was greater than 2, there were 8 solutions, right? So how do I make a equal 1, b be greater than 2? How would I check that part of it, where you found 8?
So a equals 1, a less than 2. And then b equals 2, b less than 10.
B equals 2, b less than 10. So here we're hoping for 8.
8.
And sure enough. And then, let's see, when a equals 8, I think you said there were, what was the one that had?
That was one of the ones that had 32.
Okay. So alright.
So a equals 8, a less than 10.
A equals 8, a less than 10.
B is, well, B can just be 2. Well, B was 2 and B less than 10.
Okay.
And this works.
Alright. And what are we hoping for? 32?
32.
Ooh, shoot, 56. What went wrong?
So, a equals 8. Did we just want equals to 8?
Yeah.
Oh. So a equals 8, a less than 9.
Yeah, see how easy it is to accidentally make one little small error there? A equals 8, a less than 9, this should be?
32.
32. Okay. So because the total number of cases here is less than 10,000, there's 9 to the 4th cases, which is less than 10,000. So this is easy to set up as a computer program and check our answer. Whereas on the other hand, seeing if there's infinitely many twin primes, easy to do on a computer?
No.
No. Much harder to go to infinity. This one's a good, simple, short computer programming lesson. All right, good job.